Hello again, grade 12s. Let's move on to 4, which is nuclear energy. To start off, let's talk about something called atomic mass units. Now, atomic mass units, there's an alternate form of mass that you use for nuclear reactions. They have a unit, either U or a lot of times it'll say A and U. Now, important to realize these are not metric. But we do use them a lot when we talk about nuclear physics. That's because really tiny things like a proton or a neutron, their mass is so small that having their mass in kilograms, it's a little bit awkward and weird. So this is how we come up with an atomic mass unit. We take an atom of carbon-12, we say a neutral atom with a proper number of electrons, and we say that it is exactly 12 atomic mass units because it has 12 particles in its nucleus. So therefore, 1/12 of that mass should be 1 atomic mass unit. Now the conversion factor is 1.660539 times 10 to the negative 27 kilograms. I will usually abbreviate myself to 1.6605 times 10 to the negative 27 kilograms. Now please jot down this on, make sure this gets onto your data booklet because it is not on there on this version. What is on there in both atomic mass units and kilograms are the masses of these subatomic particles, including protons, neutrons, and electrons. And if you heard that bell, I do apologize. The mass of the electron is really, really tiny. If you look at the mass, it is like less than 10,000, sorry, of the mass of a neutron or proton. So we usually just ignore it in calculations. So we're not going to worry too much about that. Oh, went the wrong direction. We're going to use this in this talk about binding energy. So this is going to be the energy that gets released in these nuclear reactions. Now, what is binding energy? Well, let's imagine a nucleus. A nucleus made of protons and neutrons. Now, neutrons have no charge, they're neutral, but protons are all positive, and they're packed close together, really fairly tightly. So because they're all the same charge, there's an electrostatic force between them trying to push them apart. Now, why don't the nuclei fly apart? Well, there's got to be something holding them together. And so what physicists called that something, they said it was an attractive force. And that was called, they call it the strong nuclear force. And again, if you heard those, if you heard that announcement, I apologize. I'm filming this at school. So we have the strong nuclear force. Now, this is a force, it is very strong, and it's only in the nucleus. Not only that, it only acts over very, 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 very tiny distances, measured in femtometers, which is like a billionth of a micrometer or something that small. It's so short range that it can actually only attract other nucleons that are right next to each other, which means nucleons that are on the opposite side of the nucleus don't affect each other with this force. It is that small. So in stable nuclei, the strong nuclear force is strong enough to hold the whole nucleus together. But there's a constant push and pull between the strong nuclear force and the electrostatic force. The strong nuclear force trying to hold it together and the electrostatic force trying to throw it apart. Therefore, as long as the nucleus is stable, energy has to be added to separate the nucleons. Move them far enough apart so the strong nuclear force can hold them together. This energy is the binding energy. Now, what this also means, thanks to Einstein's work, is that we're adding energy to the system. This also means that there's going to be a change in mass. But since energy has added to the nucleus apart, when they're apart, they have to have energy. Which just makes sense because they're more likely, they're moving around. If they have more energy, this will have an effect on the mass. So when nucleons are bound in the nucleus, and they haven't had enough energy yet, so they have less energy. And we're going to use this formula, E equals mc squared, or more accurately, E equals delta mc squared. So we're going to show that the energy is directly related to the mass. And since the separate nucleons have more energy, they must have more mass. And bound nucleons have less energy, so they have less mass. And that difference is going to be called the mass defect. So this means that separate nucleons are always heavier than when they're stuck together. And as we said, this is called the mass defect. And this is directly related to the binding energy through Einstein's formula, E equals mc squared. Now, this is when we're going to need to use kilograms, because in order to calculate energy, we need our mass to be in kilograms, so our energy will be joules. So we will be converting, when we calculate binding energy, we will be converting AMU to kilograms. So how do we find the mass defect? Well, it's actually a lot simpler than you realize. It sounds difficult, but it's actually fairly straightforward. So our mass defect is going to be equal to the mass of our nucleons minus the mass of our nucleus. Okay, so what makes up a nucleus? Well, if I take the mass of all my protons and the mass of all my neutrons, that should be the mass of my nucleons. And now I'm just going to subtract the mass of that nucleus. So all I have to do to find the mass of the protons is take my number of protons times the mass of one, and do the same thing for neutrons, and I've got the mass of my nucleons. Oh, and the mass of the nucleus, the actual mass of the nucleus should be given in your question. So to calculate the mass defect, as I said, we're going to add up the masses of each proton and each neutron that makes up the nucleus, and then we're going to subtract the actual mass from the combined mass. So let's look at an example. We're going to find the mass defect of copper 63. And the actual mass of my nucleus is going to be 62.91367 atomic mass units. Now this one, I'm also going to show you how to convert to kilogram to that. Now I need my mass of my nucleons. So I'm just going to set up the whole equation here. Now to find the mass of my protons, I'm going to take the number of protons, I'm going to multiply it by the mass of each proton. And then I can do the same thing for the neutrons. Neutrons times the mass of each neutron. And then I subtract the mass of my nucleus. Okay. So let's put some numbers in here. Copper is element 24, so that means I have 24 protons. Each proton has a mass of 1.007276 atomic mass units. Yes, we have it in kilograms. I'm going to stick with atomic mass units on this one. You'll see why in a second. I'm going to do the same thing for the neutrons. I don't know exactly how many neutrons I have, but I have 63 total nucleons, and 24 of those are protons. So I can just set it like that. And here's my mass of my proton, or my neutron, sorry. And then I subtract the mass of my nucleus. Wonderful. And I should get 0.598889 atomic mass units. Now, if I want that in kilograms, I'm going to multiply it by that 1.6605 times 10 to the negative 27. That's the conversion factor we had earlier in the notes. And I should get 9.945 times 10 to the negative 28 kilograms. Now that's going to be useful when if we have to find the binding energy. Okay, so I've got some questions here. I want you guys to pause the video for each question, and then I'm going to show you the answer. So for this one, we're just finding the mass defect. So feel free to pause the video. Okay. So my mass defect here, if I calculated that out correctly, should be 1.69636 atomic mass units. I'm just going to keep these in atomic mass units for right now. It's not asking for the binding energy, so it doesn't. Nope, I forgot my pen. Apologies. All right, now this one's asking for the mass defect per nucleon. So first we'll have to find the mass defect. And then we're going to take that mass defect and divide by the number of nucleons, of which there should be 56. So if we pause the video and do that. Okay, so I got this number. The atomic mass units from mass defect, so take that and divide by 56. And that means for each nucleon, I should get that. Again, this is the same as before. So what we'll do is we'll just pause this here and you can figure it out. All right. Mass defect per nucleon. I calculated that. When I calculated all out, I got 0.0079132 atomic mass units per nucleon. So how does this turn into energy? Well, we're going to take that mass defect and we're going to put that into Einstein's equation. E equals mc squared. So let's do that. So this is an extension of the previous example. For copper 63, we've already found our mass defect of 9.945 times 10 to the negative 28 kilograms. And we're going to put it into E equals mc squared. Please remember that c is still the speed of light. So I plug those numbers in, and I should get 8.95 times 10 to the negative 11 joules. Now keep in mind that is per atom. Okay? So that's why it doesn't seem like very much. But trust me, it adds up really quickly. All right. So for these binding energy questions, same as before. But we're going to pause. You're going to have a chance to calculate the binding energy for lead 206. And then I'll show you the answer. Okay, feel free to pause now. And that's what I got. Let's move on to question 2. Oh, sorry, that was my mass defect, and then that was my energy. My apologies. Now we'll move on to question 2. Number 2, feel free to pause. We'll find out by the energy. And that's what I thought. By the energy. And question 3. Same deal. Pause. And the binding energy. All right. But what if I don't just have a single atom? So, continuing the example from last time, I found that I had an energy, a binding energy, sorry, of 4.587 times 10 to the negative 10 joules per atom, but I have 500 grams, a kilogram of uranium. How much energy is that? So we have to convert that into numbers of atoms. We're going to go all the way back to chemistry here. And don't worry, this is the most chemistry that we're really going to do. So I have a mass of 0.500 grams. Now, the only thing I can relate to is my molar mass. Now, luckily, it's really easy to find the molar mass of this because for uranium, it's 238. Because this is pure uranium-238, the molar mass will be 238 grams per mole. Wonderful. So which means if I divide those two, I should get oh, that's actually sorry, it should be 500 grams. No wonder my answer is a little funky. 2.101 moles. Now, what does this mean? Well, 1 mole is 6.022 times 10 to the 23 particles, in this case atoms, per mole. So if I multiply those two together, I should get a total energy, total number of atoms of, where is it here? Up here we go, 1.265 times 10 to the 24 atoms. Now, since each atom has this many joules of energy, if I multiply those together, I will get a total energy of 5.80 times 10 to the 14 joules, which is how much energy it would take to power a house for about 18 years. So pretty impressive. All right. So the next thing you've got there is some practice. As you see, I've got the answers posted up here. You can skip number 10. Yeah, you can skip number 10. Oh, and the answer for number 11 because it's a concept question. So if you have any questions or concerns, feel free to get in touch with me as soon as you can. Other than that, we'll see you in class. Bye.